இது 20,000 அட்வான்ஸ் கேக்குறாரு. எடுத்துக்கடா.
Audible.
ఇంకొచ్చి
Audible.
Yes, sir.
Yes, sir.
Great. Okay, dear. Now this transformer, phasor diagram and equivalent circuit. Then there is a question in which they give the no load parameter and the load parameter. Then they ask the primary side power factor and current. So I think you understand how to calculate. Okay. Any doubt? Yes. Please. Here we discussed this transformer types and working principle, equivalence. Now ideal transformer, which has a no leakage flux, winding of infinite permeability, reluctance is zero of the core. Then winding has a no resistance, means zero impedance. Okay, no magnetic losses and copper loss. Correct. Then this is the phasor diagram of at no load ideal transformer. Correct. Here only magnetizing current is there. Okay, this audible. So this is your transformer. Here, see this E1, E2, they depend. This is a flux. Due to this flux, the induced voltage and current. V1 is the supply voltage here. V2 is output terminal voltage at load. Now at no load, it is equals to induced voltage E2. Now here this Im is, we denote is I mu, magnetizing current. That equals to I. At no load, this I1 equals to I naught. Correct, no? Now this is the phasor diagram when we consider the magnetizing branch at no load. So there is a I naught current, I naught. Okay. This is I naught has a two component now, omega and mu. Okay. Now due to this flux produced by I mu, the induced voltage E1 and E2. Got it? Magnitude is depends number of turns, but they are in same phase. Okay. Now at load, here we consider the no voltage drop in winding, means impedance we neglected, primary and secondary. Therefore, induced voltage equals to terminal voltage. Okay. So this is the diagram which is used in numericals to calculate. Okay. Got it? This is the leakage flux we discussed and your equivalent circuit at load. Now at unity power factor. Now here we consider not neglect the resistance and leakage reactance. Due to both, there is a drop. See, at unity power factor, this is your E2, this is your V2. Now current in same phase. Due to this current, there is a drop in resistance, drop in reactance. Similarly, there is a drop in primary due to this primary current I1. Okay, and reactance drop. Correct. So this is at unity. At lagging power factor, see this I2 is lag by B2. At leading power factor, your current is lead. Okay. This vector diagram that not asked you, but no load condition you know. Okay. Now this is the equivalent circuit at no load, your only magnetizing branch. So this is the two component of your no load current. From no load parameter, we not calculate the R naught, X naught. Okay, magnetizing branch. You know the voltage across R and X, it is V1. So we can calculate this current. If we know the current, we can calculate. Okay. This is the equivalent circuit of transformer. Now, how we transfer the parameter from primary to secondary side or from secondary to primary side? As referred to secondary side, as referred to this is, and as referred to primary side. As referred to primary side, as referred to secondary side. Okay. Now, hello, readable? See here. Now, how we transfer the parameter? Suppose we transfer this parameter from C, as referred to primary side, means this secondary circuit parameter we transfer to primary side. So this is your, as referred to primary side, this is the resistance R2 dash and this is X2 dash. Now E2 dash equals to E1. Okay, because here across this this branch, it is E1, and you know it is E2 dash equals to E1. Here V1, then I1, X1, R1 is the primary side leakage reactance and resistance. Okay, this is I2 dash, X2 dash, R2 dash, X2 dash, then E2 dash, V2 dash, ZL, load impedance. Okay, dear. Now you know individual circuit of transformer, you know, as primary side you have a resistance, then leakage reactance. A minute. Hello, audible? Yes, please. Hello.
Audible, sir.
Yeah. So this is your individual. This is your primary side. Okay. This is your secondary side. Now these are individual parameter of primary side, secondary side. Now this is your load impedance. Due to this load, there is a load current I2. And suppose it depends what is the power factor. It is unity or it is lagging, leading, whatever it is, cos phi 2. Okay. Now overall power factor is primary side. It is cos phi 1. Okay. Now please, age refer to secondary side, means this parameter, this will be your equivalent circuit in this case. Okay. Then how we transfer the parameters like I2 days. So you know your turn ratio, this in practical transformer means actual ratio is I2 days by I2 equals to K. Then we have calculated na I2 days. Therefore I2 dash equals to, as referred to primary side, it is KI2. So means if we transfer the current, it is multiple with K. Now V2 by V1, E2 by E1. And your voltage, if we transfer the voltage, like your this E2 by E1 means E2 days, that is E. Here it is written E2 days equals to E. So in your turn ratio, this E2 by E1 equals to, means this, okay, equals to K. Then therefore E2 day, you know this E2 days equals to E2 by K. So means if we transfer the voltage, or similarly you can write V2 days equals to V2 by K. So your current is multiple, voltage are divide. Now we coming to this resistance and impedance. Okay. Now when we see individual total copper loss in transformer, total copper loss, losses, you know, in primary, this is the primary copper loss, in secondary, or as referred to primary side. When we reduce this also, this magnetizing branch transfer at supply end, then final equivalent circuit will be, exact equivalent circuit is like this. Okay, not exact, it is equivalent, approximate equivalent circuit. Here, this now if we transfer this magnetizing branch here at supply end, then only difference is this voltage. Okay, so there is nothing major difference between E1 and V1 due to this drop. So if we transfer this magnetizing branch at supply end, no major change in the performance of transformer. Okay, then see this both resistance are coming in series. Okay, and both reactance are coming in series. Okay, therefore total equivalent resistance and total equivalent reactance as referred to primary side, it become now R01. This become X01 as referred to primary side, total equivalent. Then your load impedance is shown here. Okay, ZL dash, this is V2 dash. Okay, here you know this is your E2 dash equals to E1. This is your, here it is your V1. Okay. This is your V1. Okay. This is your I1. Now at this node, this is your I node. Here it is your I2 days. Okay. This is two current. Hello. I omega I mean magnetizing current. Okay. R naught X naught. Okay. Anything else? No. Correct. Now this is actually this is your total equivalent. Hello, please you take it seriously. There is a numerical is asked on. Okay. Now this represents the total impedance as referred to primary side. Now this is the total internal impedance of your transformer. Now drop in this impedance. Okay, if there is no load, then this terminal voltage equals to your induced voltage. Okay. Now here this is actually B1. No? Here E1 means B1. Okay. Correct. Okay, dear. Now you know what is the voltage regulation. The percentage change variation in this terminal voltage from no load to full load. So what is the what is this V2 days at no load? At no load. What is your V2 days? Equals to E1 or E2 days equal, that is V1, correct? And at, suppose when there is a full load, okay, at cos phi 2, lagging power factor, this is the load current, okay? At full load, okay, when there is a secondary load current is there, then this terminal voltage reduced to secondary terminal voltage. Okay, this at no load. At full load, what is the secondary terminal voltage? Now it is become V2 days. So there is a change na? Hello, at no load, at full load. Now percentage regulation. What is the definition of percentage voltage regulation? Change in output terminal voltage from no load. What is the no load voltage? V2 days minus V1 correct na? Sorry, this is wrong. Just a minute. Hello, this at no load, no load terminal voltage. What is the no load terminal? V1 minus at load, it is V2 days. Divide by with respect to your no load terminal voltage. Please remember always, because it is constant. So divide by V1 into 100. This will give the percentage voltage regulation of your transformer. Okay. As referred to primary side. Okay. When we consider this parameters. Now how we transfer this. Now as referred to this equivalent circuit, what is the total copper loss? This total copper loss I1 square R1. This will be represented by this also can be given by total copper loss. We can represent by as referred to primary. What is the load current of transformer? Please, we neglect this only. Okay. Suppose we neglect this, then I1 equals to I2 dash. Okay. So this I1 as referred to primary side. I1 square R01 will give the total copper loss. That should be equals to I1 square R1 plus I2 square R2. So see, then we calculate R01 means I1 square I1, it will be I1 plus I2 by I1 whole square R2. You know, I2 by I1 is, hello, in the transformer turn ratio. E2 by E1 equals to V2 by V1 equals to I1 by I2 equals to K. Okay, and that is N2 by N1. So see, it means then if we do I2 by I1, it is means 1 by K. Okay, we can write R01 equals to R1 plus R2 by K square, because it is a square. Okay, R2 by K square. And this R2 by K square, we can write R1 plus R2 days. So what is the value of R2 days? R2 by K square. K square is the turn ratio. Got it? R2 by K square. Okay. Similarly, we can calculate total reactance, that is X1 plus X2 days. Then X2 days equals to X2 by K square. Similarly. Okay. Similarly, your impedance Z2 days or ZL days. Okay. Like Z2 day or ZL days. It means you are, now you please remember, hello, when we transfer the parameter, secondary parameter to primary side, current is multiple with turn ratio, voltage is divided by turn ratio, resistance, reactance, impedance, they are divided by K square. Okay, please. Now similarly, now we come to the next part, okay, of this question. This, if we transfer, as referred to secondary side, when we transfer this primary side parameter, hello, sorry, here we draw now this. Now this primary side parameter, here in primary, there is a magnetizing branch is also there. Correct, no? Please resistance and leakage reactance, then here you put the magnetizing branch also. Okay. Okay, this is your R0 X0. Correct. This is I naught. This is I2 days. Now, as referred to secondary side. In secondary side, you have transfer this. See, all like it is I1 days. Here it is a forget. This is I1 days. This is V1 days. R1 days, X1 days, Z1 days. We can write R0 days, X0 days, I0 days. Okay, so this is I1 days here. At this node, this is I naught days. I naught days. Okay, and this has a two component. I omega days, I mu days also. Okay. Now this is your secondary side. So we write I2 X, R2 X2, V2 Z2 or ZL. So this branch is, hello, this portion is we have to transfer from primary side. Okay, that's why they are denoted as dash dash. Now come to now again same. If this magnetizing branch we shift here, okay. So your exact equivalent circuit means approximate equivalent circuit will be total resistance, total reactance, and this magnetizing branch we shift at terminal supply. Okay. This is your load, ZL. Now here, this terminal voltage is V2. V2, okay. This is R02, X02. Total equivalent resistance as referred to secondary side. And this is total impedance as referred to secondary side. Hello. As referred to total equivalent resistance, total equivalent reactance of transformer as referred to secondary side. Okay. Now at this terminal supply, here we apply V1 dash as referred to prime secondary side, V1 dash. Then at this node, this is I naught dash. X naught, sorry, it is R naught dash, X naught dash. This is current also dash dash, okay. Here, this is I2. This is your load current I2 at cos phi 2. This is V2. Now, due to this load current I2, there is a drop in this impedance. Now, what is the this here? This is E2 equals to E1 dash. Here we put E1 dash. Okay. So now, as referred to secondary side, this no load terminal voltage. Hello. So at no load, this output terminal voltage at no load, secondary terminal voltage. What is your secondary terminal voltage? V2 equals to E2 at no load. But at full load, or at load and load condition, we take at rated load. What is the secondary terminal voltage? Secondary terminal voltage equals to V2. Then there is a variation in the voltage, terminal voltage at no load and full load. So that is represented as like here, due to full load, when full load current is flow. At no load, if we remove this load, hello, if you remove this load, correct, then this current is become 0. There is no drop here. But when there is a load, due to this there is a drop, then it means this voltage is now reduced to V2. Otherwise it is E2. So therefore percentage internal voltage drop as a percentage, that is called as a percentage regulation. So this voltage regulation as referred to secondary side, you know, from no load to full load, terminal voltage, no load terminal voltage minus full load terminal voltage. With respect to full load you calculate. Sometimes it is E2 minus V2 by V2, rated terminal voltage with respect. Okay, this is called a down and up voltage. We use this with respect to no load terminal voltage. Okay, then it is okay. Into 100. Okay, so this is your percentage voltage regulation. Okay, generally you as refer to secondary side, because secondary side is a load side, so we use this formula. But sometimes they give the as refer to primary side parameters, then we use this formula. Okay, this, okay, this is also same, no load terminal voltage, full load terminal voltage divided by no load terminal voltage. Okay dear, now come to Okay, now here, how the parameter is transferred? Hello, here equations will be changed. Age refers to secondary side. When we transfer the parameter from primary to secondary, then you know what is your I1 days. Now current is multiple by. See how? Because we write now this I1 by I2 means I2 equals to K. So here we replace this I2 days means this is I2 days. Okay. Sorry, I2 means this is I1. Here we neglect na. Generally I1 equals to I0 plus I2 days. So if we neglect this, then I2 will be, this is as referred to primary side. And this side I2 days. 1 by I2 days. Yes, we write this I1 days equals to Ki2. Now parameter are changed. Okay, it is just opposite to your as referred to primary side. Okay. Hello. So as referred to the secondary side, your current I2 days equals to Ki2. Okay, it is divide, no, sorry. As referred to, okay, it is divide, no, current I1 days means I1 by I1 means I1 days means then it is I2, no? Okay. I1 days means if we neglect here I0, then I1 days equals to I2, correct? And your turn ratio is I1 by I2 equals to K. Now this I2 is replaced by I1 by I1 days. Therefore, I1 days equals to K, na? This divided by K. Okay, I1 by K. So now, as referred to secondary side, your current is this divided by K square. As referred to primary side, hello, here current is multiple by K. I2 days equals to KI2. But here I1 days equals to I1 by K. Okay, so here please remember this. Okay, now voltage, this is talking about the current. Now voltage, like your V2 days, sorry, V1 days. Now current is divide, then voltage will be multiple, like V1 days equals to KV1. Same like E1 days equals to KE1. Okay, dear. Now we come to the same like your resistance and reactance, you know. Now total copper loss will be as referred to secondary side. This is your total resistance. Current is I2. This is square equals to again total copper loss in individual windings, R2. Then this R01 equals to this divided by this, then you get a R2. But when this divide, I1 by I2 whole square. I1 by I2 whole square into R1. This is K. You know, in your turn ratio, it is K. It means this is 2. R02 equals to R2 plus R1 days. And R1 days equals to R1 K square R1. Please, so your resistance is multiple. Resistance, reactance, impedance, they are multiple by K square. Hello. Now you go get the difference as referred to primary side and secondary side. Hello. So similarly, your reactance will also multiple by K square. Then Z1 days also K square, Z1 like this. Okay. If you know this, no? Okay, dear. Any doubt, please you can ask. Hello. Okay, current is divide, voltage will multiple by K, resistance, reactance, impedance, they multiple by K square. Okay. Same like this also, R0 days, X0 days, I1 not days, everything. I1 days, so already we can know. This also, we use this K square R0. This is not I0 dash. This is also K square X0 and I naught days. I naught days. If you calculate I naught days equals to, now for current it is divide. So your I naught divided by K. Please remember, okay? These things we can transfer. Same like you also transfer the I mu days and I omega and I mu days also. Use this current relation. It is divide by K. Anything left? Hello? Please. Got it? So here this show the relation, how the transfer, okay? Okay, dear? Now we come to the voltage regulation. Actually, you know the formula of voltage regulation. Terminal voltage, change in the terminal voltage from no load to full load with respect to your load terminal voltage, okay, as a percentage. Okay. Now we can calculate this by your phasor diagram. Hello. Here. We use this circuit. Yes, please. Now, if we draw, suppose we consider this power factor is phi2, load power factor. Hello, this load power factor we consider phi2. It is a lagging power factor. Okay, at lagging power factor. Okay. Now we draw the secondary term, this equivalent circuit, or what vector diagram. So now from phasor diagram, from equivalent circuit, this is total equivalent circuit, we draw the phasor diagram. See, we take a V2 as a reference voltage, means reference phasor. Here, just here, right? Flow. So this is suppose your voltage here like this. Okay, this is your V2, correct? V2. Okay, at 0, it has a 0 reference vector. Now due to the V2, this load current will be at lagging power factor. cos phi 2, cos phi 2 is your power factor. Then we can calculate phi 2 if they give the power factor. Equals to power factor. Then we can calculate phi 2 equals to your cos inverse of your power factor. Then you get angle. Suppose 0.8 is the lagging power factor. Then your angle will be 36 degree. Okay. So this load current at lagging power factor is lag the voltage by phi 2. Okay. Now, as I told in RL series circuit, always drop in resistance. Hello, in resistance, if suppose some current is flow, and this is R, the voltage drop across this resistance VR, it is in phase with current. Phase with means it is in phase with the current, means it is parallel to current. But it is a voltage, that's why we add with this voltage, okay? So this, due to this current, there is a drop in resistance, that is I2 R02, total equivalent resistance, total drop in resistance. Similarly, suppose there is a reactance, the drop in reactance, inductance, reactance due to this, it is perpendicular to this voltage drop. Like here we write it is VR, then VL is like this, perpendicular to this current. Okay, so here it make a 90 degree angle, this drop, reactance drop. Okay, like this. This is your I2 X02, total reactance, drop in reactance. Okay, any doubt, please? Now, my dear, here, see, this voltage plus this drop across reactance, drop across resistance. It will give the total voltage across this terminal. What is the voltage here? Hello? Now, simply you see, what is the voltage before this reactance? Here, that is E2. E2. And here at load, it is this V2. Okay. So if we add this all three voltage like V2, then this VL, this VR voltage across this, okay? If we add this voltages, okay, this total vector sum of this all three voltage, this plus this plus this, this plus this plus this, we get a total sum. Okay, this will give you G2 phasor. Any doubt up to here, please? Hello. So this is your no load terminal voltage, correct now? Hello, this is your no load terminal voltage. This is your load terminal voltage, correct now? V2. Okay, dear. V2, E2. Okay, dear. Hello. Any doubt? Now, we have to do some geometrical work. What we do? You have to take a compass, put a needle here, and draw a circle of radius of E2. E2 radius का एक circle draw करेंगे. Right. Okay. Hello. This is the circle we draw. Correct. Now, at any point of this circle, this radius will be constant, no? Okay, so just we extend this vector, okay, up to here. So this length also, this length, this total length is also Hello, please tell me, this total length also give you E2, correct now? Let us we calculate this distance. Now, please put a one perpendicular here. This is 90 degree, yeah? Okay. So if we extend this and we put 90 degree, now please, hello, this vector is parallel to this, and you know this is 0. So this will be same angle phi 2. And now this is 90, this is 90 minus phi 2. Then this is also 90, then this angle will come phi 2 also. No, 90 minus phi 2. Sorry. And this come 90 minus phi 2. This is also 90 minus phi 2. Now please draw a one perpendicular here. Hello. So only this small portion. Yeah, this entire length from here to here, this is I2 x02. Okay, here we write. Now, please. Sorry. Now we calculate. Hello. Yes, please. This three distance we require. This, and this you know, huh? Please. Hello. This is V2. And you know what is this? Hello. If you take a hello, see this horizontal component of this vector. This will give you hello. This will give you. Please. What is this value come? This comes I2R02 cos phi 2. And you know, this make angle here. This will be, hello, if we do solve, no? This is also 90. This is 90 minus phi 2. Then this angle will come phi 2. Please remember, this angle is phi 2. This also come phi 2. Now, this angle side, if you do this side, na, it come cos. Hello, if we do the vertical component, it comes cos theta. If you do this horizontal, hello, along this, no? What will come? It comes I2 x02 sin phi 2. Please remember. And ये small portion हम छोड़ देते हैं, neglect this, neglected. Okay. So what is this E2 will come? Hello. What is the equation for E2? Means vector sum. This E2 will be from this phasor diagram, from phasor or vector diagram. Okay. Please. E2 equals to V2 plus this is vector sum. I2R02 cos phi 2. Phi 2 is the power factor. Then plus I2 x02 sin phi 2. Any doubt here, please? Because see, this three vector come together, this plus this horizontal. Now it is not a vector, it is like simple algebraic sum will come. They are in same page, no? Horizontal components. Okay. Got it? Hello. Now we write therefore. So this is your E2. Okay. From this. Now we calculate therefore voltage regulation. Hello. That is by definition E2 minus V2 by E2 per unit. Now if you subtract E2 minus V2, then this will cancel. E2 minus V2, what is the, or either you take this vector this side, then it is E2 minus V2. Therefore, we can write E2 minus V2 equals to I2R02 cos phi 2 plus I2 x02 sin phi 2 only. So means this is I2 R02 cos phi 2 plus I2 X02 sin phi 2 divided by E2. This is your voltage regulation, percentage voltage regulation. That is, you have to multiple with 100 only. Okay. Okay, ideas. So this is your voltage regulation here as referred to with respect to your second, as referred to secondary side. Okay, any doubt here, please? Now you know, hello, this I2 is your load current, cos phi 2 your load power factor. If you know the cos phi 2, you can calculate sin phi 2 also. Okay, sin phi 2, cos phi 2. Then you know, here E2 you know, no load terminal voltage. V2 you know, full load terminal voltage. Then R02 is the total equivalent resistance as referred to secondary side. X02 is total reactance as referred to primary side. That is R2 plus R1 days. This is X2 plus X1 days. Yeah, now you know I1 days equals to what? X1 days equals to what? That is multiple by K square as referred to secondary side. As referred to secondary side, they are multiple by K square. Okay. So this is K square R1. This is K square X1. Okay. If you know this parameter, we can calculate the voltage regulation. Okay, dear. Any doubt here? Same, this voltage regulation we can calculate from this phasor diagram. Again, we suppose we take a load power factor is cos phi 2 here. Okay. Here also, you know, if you draw the vector diagram, this is your V2. This is your V2. Okay. Now at lagging power factor, your current is lag. Now X of V, not V2. Now as referred to primary side, we write this is V1. Correct, no? As referred to primary side, this is your V1, this is your I1 load current. Okay. Now this is your phi 1, means power factor. Generally, now here we take a cos phi 1 is the power factor of transformer. Transformer power factor. Okay. Then we can also calculate phi sin phi also. Okay. Now, due to this current, there is a drop in resistance, equivalent resistance is R01. So this is in phase with the current, no? Parallel to current. It will be your I1 R01. Then this is your I1, here you write I1 X01. Okay. Then this total. This is your E. Now it is your what it is? E1. E1 means V1. It is E1. Okay. It is your E1 or V1. Hello. It is your. So what is the voltage here? That is your V2 days. sorry, this is your V2 days. Because here, no, this is your V2, okay, please, V2 days. Just a minute, okay, just a minute. This is your V2 days. Then please here also we neglect this no load current, okay? So here this actually it is I2 days. And this is phi 2 days, we can write power factor. We take a cos phi 2 only, okay? Because this is second side. Hello? V2 days, I2 days. I2 days we assume as it is I1 because no load current is neglected in as referred to secondary side also. Now this is V1 or E1, okay? No load terminal voltage. This is load terminal voltage, okay? Now again same, you draw the here circle. Then we extend this again same like this. Again here this perpendicular line same like, okay, this. So what is this distance? This distance, this is phi 2 again, this is also phi 2, okay? Please, this is V2, this is, you know, I1 R01 cos phi, either you write 1 or 2, okay, not issue. This is I1 X01 cos phi 2, sorry, sin phi 2, this is sin, this is cos. So like here also, what is your V1 or E1? Hello? That is V2 days plus I1 R01 cos phi 1 or phi 2, okay, cos phi 2 plus I1 X01 sin phi 2, okay. Now voltage regulation. Now voltage regulation, as I told, no load terminal voltage minus load terminal voltage divided by no load into 100 as a percentage voltage regulation. Okay. So if we subtract, this will go to only I1 R01 cos phi 2 plus I1 X01 sin phi 2. This is your regulation. Divide by with respect to V1 into 100. My dear, this is your formula which is used as referred to primary side. Very important. Why I explain this? Hello. Due to leakage reactance, you have to draw by explain the effect of leakage reactance on transformer performance or voltage regulation with the help of vector diagram. So please you draw this vector diagram as referred to secondary side. You take the example and you write this. Then here see, if your leakage reactance is high, more will be your reactance drop. Then higher value of voltage regulation is not good. It is bad. Poor regulation. Poor regulation means higher voltage drop. Okay. Now your voltage regulation, it depends on power factor. It is lagging, leading, or whatever it is. Okay. Correct. I explain in this equation. If this equation is for lagging power factor. If it is your power factor is leading, then this sign is come negative here, my dear. Okay, please understand here. In this equation, at leading power factor, it comes negative in both cases, okay? Either you take as per this also. So at leading power factor, this comes negative sign, okay? Now, if we talk about the unity power factor, suppose if you are cos phi 2, hello, if you are this power factor, this load power factor is unity 1. Unity means only resistive load. Then my dear, this phasor diagram is changed. Even in leading power factor it is changed because we not draw, but here see this current will come this side. It lead this voltage. Then if we draw now, this equation will come negative sign. Okay. Now at unity power factor. At unity power factor, this is your voltage at unity power factor. Please read. Okay. It means cos phi 2 is 1. Then phi 2 equals to cos inverse 1 means it is 0 degree. Your phase angle is 0. It means, suppose this is your voltage. It's voltage V2. Then your current is in phase with voltage here. Or either you show with red. This is your VI2 as ever to second is that. Because phi 2 is 0 degree. Now due to this current, the drop in resistance is not 0. Resistance and reactance, this internal reactance, it is not a load impedance, load reactance. Hello, load is your pure resistive, but this internal resistance reactance will be there. Okay. So here, the drop due to this current in resistance in phase with current means it add here in like this. So this part is your due to drop in resistance. Hello, that we can write I2R02. Now due to drop due to in reactance, it is perpendicular to this drop, that is I2X02. Now we calculate the vector sum of this series. This is your E2. Okay, please. Now this, this voltage, and this and this, hello, this part, this part. Okay. So in triangle OAB, OB square equals to OA square plus AB square, correct, no? Or it is E, we calculate the E, E2, this is E2. E2 means we have to put the under root. OA means this, it is V2 plus I2XR02 whole square plus I2X02 whole square. This is your E2. Then percentage voltage regulation, you can write E2 minus V2 by V2 or E2. Okay. Got here in 200. This is your voltage regulation at unity power factor. This equation will change. Okay. Any doubt? If someone is give the question like your circuit parameter and they ask the voltage regulation, you can solve. Why I explain this all the things? Question you can, they can ask. The last time there was a question is asked in your exam based on this. This here the first part. Hello. Leakage, how it is implied, how we take into account of analysis. So you can explain due to leakage flux, leakage reactance there, and there is a drop. Due to drop, poor regulation, current will be high, then further losses will increase, then your efficiency and performance of transformer is Now, this we talk about this question, very important. This is the conclusion of today's class. Okay. Great. Now here, this was a question asked recently in your exam paper, huh? Please. Yes. The following result are obtained on a 50 kVA transformer. So your transformer is single phase transformer, huh? This transformer. When here we apply the primary, you apply the rated voltage V1, that is 415 volt. So it is here not written, it is 3 phase, no? It is not right here. He not talk about the phase, it is 3 phase or single phase. Okay. So we take as a, it is your voltage is V1 is this, correct? Okay, and it is 50 kVA. 50 kVA is your rating transformer. Okay, now we do the testing on. First we run this transformer at no load. Means we do the open circuit test and short circuit test. What you do in open circuit? We apply, he said that in open circuit test, the primary voltage V1, this primary voltage, we apply the, on HV side, we apply the rated voltage. Here, V1 we apply 3300 volt on primary side. Then this kept is open. What is the voltage induced here? 415 volt. We measure with voltmeter, okay? Here we also measure. Then we measure the current and power drawn by transformer. Okay, we can put here wattmeter, then we measure the power. So what is the primary power, input power? Under open circuit test. Open circuit test data is open circuit test. V1 is 3300. V2 means it is also you consider as a E1 because drop we consider 0. So it is E1 equals to V1 or here E2 equals to V2. It is 415 volt like. Okay. Then it take your no load input power, that is 430 watt. You know, no load input power equals to core loss of transformer, core losses. Okay. Now add short circuit test. You know, in short circuit test, we short this secondary terminal, LV side terminal with a bus bar. And here we measure the current here in short circuit, because in short circuit voltage becomes 0, but we measure here, we measure the voltage, this open terminal voltage, voltmeter. Here we measure the current, that will give you short circuit current, okay? And here, now in short circuit test, in primary we not apply the rated voltage, we apply reduced voltage. Reduced voltage, that is called VSC, means voltage under short circuit test, applied voltage on only 124 volt on LV side, okay, on primary side. Then how much voltage is applied? So that primary current will flow here. This transformer primary power and primary current. So this is your straight, the current is full load 15.3 ampere under short circuit. Okay. This primary power in this case, hello, under short circuit test. Now power input is considered as a total. It will give the total copper losses. Okay, because core losses are neglected in short circuit test. Why? Because your core loss are depends, as I told, core loss depends on voltage and frequency. So here we apply the reduced voltage, only 24 instead of 33 volt. So at this less voltage, less copper core loss. Core loss means magnetic loss. So they have neglect. Okay. So only we consider under short circuit test, total power we consider as a copper loss. Okay, copper losses. And because your transformer primary current is take as a full load current. See here what is the secondary current to be measured at full load value here. This will give the full load current, like short circuit current is when it equals to full load current, we stop to rise the voltage. We rise this voltage up to this level when till your secondary reach the full load current. So like virtually we load the transformer. Okay, we create a full load situation, but there is no load on secondary. We short the secondary, and we try to flow the current, full load current. Okay, when full load current is flowing, so actually it gives the full load condition. Now the copper loss, this will give you copper loss at full load. Okay, then full load copper loss is primary input power. Input power is your 525 watt. So this is your full load copper loss. Please remember, short circuit input power is considered as a copper loss, and open circuit condition your input power is considered as a core loss. Core loss, that is represented as a iron loss. Okay. Next. Now he says that calculate the efficiency at full load and half load, and you consider the power factor is 0.7. Very nice then. Hello. Now first part of this question, efficiency of transformer. Please. At full load, again at half load, at half load, at full load. So what is your full load? You know, we may calculate the full load output and input. Okay, then efficiency. What is the output? Transformer output or kilowatt output of transformer at full load. That is your full load capacity. Hello, that is kVA rating. kVA rating into power factor. Got it? Any doubt? So it is 50 kVA into power factor is at 0.7. What is the kilowatt output of transformer? Full load. Very easy, my dear. It is 35 kilowatt. Now you calculate, this is the output. Now we calculate input. Kilowatt input of transformer input power, kilowatt input power, you can write power at full load. Please, your output, kilowatt output plus total losses. Now, my dear, output we have 35 plus your total loss means iron loss plus copper loss at full load. Hello. Only two type losses in transformer, you know. Now it is kilowatt. So please you consider the iron loss. Hello. This is your core loss, iron loss. So in kilowatt it is 0.43 only. And copper loss is 0.525. So what is the kilowatt input? 65 plus 0.43 plus, sorry, 0.525. I dear it 35.955 kilowatt. Therefore, efficiency at full load. Output by input into 100 at full load. What is the output? 35. What is the input? 955 into 100. Please. $97. Okay, now at half load. My dear, because iron losses or core loss remains constant. You know that iron losses are called constant because they not depends on load. At half load, full load, no load, they are will be same. So this is your will be same 430 kilowatt. Okay. Okay. And at half load, your copper loss at half load, that will be 1/4. Hello. At half load, that become 1/4. Or
Sir,
yeah.
so in the question, it is not mentioned whether the iron losses or copper losses. So, how to assume that?
I told na in short circuit power is considered as a copper loss. And you know why we testing this transformer test? Why we do the testing of transformer like open circuit and short circuit test? And what they give this test result? What they show? To calculate the performance of transformer. Hello. Generally, to test this transformer. Hello. If we test physically, we have to need the load. But in your factory, when we test the transformer, it is we have required a load bank this much. Then from where we arrange the load? Suppose we arrange the load. Then the unnecessary there is a power loss in this load. Unnecessary we put the load. We waste the energy in testing of transformer. That's why there was an indirect method of testing. What we do? We do the open circuit test, means we run the transformer at no load. That no load input is very less. See, this 50 kilowatt kVA transformer at no load only take a 430 watt only, less power. Now, short circuit test, when what we do, we short this secondary. Okay. So at no load, there is no current in the secondary, but when we short this, so like short circuit test, if you apply here rated voltage, then it transformer is burn because it there is a use short circuit current will flow. Okay, so we not come on that situation. We just here apply reduced voltage. This is the condition for short circuit test. So we apply the reduced voltage, we vary this. Actually by auto transformer, we vary this voltage at a particular the voltage. This short circuit current, secondary current equals to when it will read the full load current. Then we stop to rise this voltage. Then we note down the reading. What is the input power? What is the here secondary current? Voltage is 0 at circuit. Then if your transformer, it take the full load current at short circuit test, means there is a losses because it take the power input from supply. But where this power is go, we not get anything output. So we consider the input power under short circuit is considered as a copper loss. Please remember. So you are from short circuit test, we get the power input is considered as a copper loss, full load, copper loss. And power input in no load condition, because in no load condition, that no load power input is considered as a core loss. Hello.
Yes,
Here
yes, okay, okay, sir.
now you come to this testing of transformer. Hello. Open circuit. See here, why we test the transformer? To calculate, first to obtain the transformer equivalent parameters, then core loss, copper loss, and efficiency regulation. Okay. So like here it is written, open circuit test mein this core loss equals to no load input. What it give? No load or core losses. No load parameters. Then at no load only magnetizing branch is there, na? Then in next, see, short circuit test will give you full load copper loss. Hello, it is written here, my dear. And this parameter we calculate. That's why we do the testing. See, input voltage, current and power is measured. Got it? So just read the fundamental. Okay, now got it? Now come here.
Yes, sir, no understood.
And you know why this 1/4 this become a 1/4? As you know now, hello, if suppose you calculate a load current, hello, full load current of transformer. What is the load current? If you know the load kVA, full load kVA, full load current means full load kVA means rated kVA, kVA. Divide by your terminal voltage into, if kVA then no power factor is come. If it is kilowatt then in power factor, okay, cos phi. So here only V2, correct na? This is your current. Now you know this is your current, okay, at full load. Now if we calculate a full load copper loss, as refer to secondary side. So you take a I square R02, correct na? It is a square time of load current. Now at half load. Half load means this kVA rating become half. Suppose it is here 50 kVA. But at half load means there is only half of the rated capacity. It is 25. Then divide by V2. So as compared to this and this at half load, okay, at half load, this current become half because voltage is not changed, only this. So at half load, your this I2 will be at half load is reduced to half of your full load current. Just a minute. Okay, so it is half of the full load. Okay. Now if we put at half load, then if we calculate copper loss at half load, then it is as compared to this, they become square time of, means this I2 by 2 whole square R02. So it become a 1/4 no, of your I2 square R02. It means full load. It is your half of your 1/4 of your full load copper loss. If we suppose take at 1/4 load, suppose only 1/4 load is there. It means your current become 1/4, then your copper loss become 1/16th time square of your load. Okay. Got it? Why this copper loss become 1/4 at half load? Okay. Hello. Hello, please. You're getting or not? Yes, please. Hello.
Iron losses will be constant, sir, right?
Yeah, same. But copper loss, that is your 0.2525. 525. It means they become divide by 1312 kilowatt. Now at half load here, if you calculate now what is the kilowatt output? Kilowatt output of transformer. So it is now half of your rating. Or either you write your KVA rating, rated KVA divided by half into power factor. So it is 50 by 2 into 0.7 means 25. They become 17.5 kilowatt output at half load. Now we input power at half load. So my dear, very simple, output plus iron loss and copper loss at half load. Please remember, always we write the load condition along with copper loss. Okay, so it is your output is 17.5 plus 0.43 plus 0.13125. So what is your output then? It comes 35.43 watt kilowatt. Okay. Therefore, efficiency at half load. Good question. Huh? So kilowatt output is 17.5. अरे ये wrong है.
18.06 आ रहा है सर.
Sorry. This is decimal. 15.5 plus 0.43 plus 0.13125. 18.06 0.06. This is clear now. This divided by 18.061 into 100. Um, 96.89% efficient. That's why I told every equipment, alternator, transformer, motors, they give the higher efficiency, means best performance at full load conditions. Okay, if you reduce the load, your efficiency is reduced. Okay, got it? Now first part we have calculated. Now in second portion, now here, hello, voltage regulation at this power factor 0.7 you assume as a leading and lagging power factor. So you know voltage and secondary terminal voltage corresponding to this. So actually it is asked the voltage regulation. You calculate the voltage regulation, then you subtract the percentage drop, then you get a. So third is very easy. After you, but before third you required this calculation. Okay, so very easy. You know the power factor, cos phi 2, 7, then sin phi 2. Now we required parameters, circuit parameters, R01, X01, Z01, correct? No? So, you know, hello, both case mein, this input power is given. Okay, so you know in primary side, we know in short circuit condition, we can calculate, you know, from copper loss. Hello, copper loss is R0, sorry, ISC square R02. And, you know, primary side, sorry. This is also one, na? Your primary current, so it is like rated current only. Hello. So this input power, primary power given, that gives the copper loss. Like here, I1 square R01, that will give you 525 watt. Then my dear, we can calculate R01 equals to 25 divided by current is given 15.3 square time you divide, then it come in ohm. Now R01 we calculate. Now another thing, this Z01 total, you know, if we apply the voltage at short circuit voltage divided by short circuit current, input current, this voltage is given. Voltage is given 124 volt in short circuit and divided by current is 15.3. This will give the voltage by current impedance. Then from this impedance you calculate X01. Hello, that is Z01 square minus R01. Now you get this R01, X01. Then you put in this formula. Hello. Please you try, tomorrow we will solve otherwise. See here, this he is asking in leading leaking. As refer to primary side, equivalent circuit we get R01, X01. So please you use this, okay? And one at lagging power factor you use plus, at leading it is minus. These things are there. You get this all the things. Now you know I1. You know the R01 power factor 0.7, then you get everything is available now. Okay, please just you put this formula. Okay, yes, please understand. Please you solve today, otherwise you not able to solve. Okay, tomorrow we discuss. Okay, dear. Good night. Now you solve easily. this question. Second part, you have second and third easily you can find out, okay? Or tomorrow we will complete, okay? Got it? Please revise this portion. It is very important, okay? Hello, audible?